Hello students, welcome to EPG Pathshala. I am Dr. Ajit Kumar Mahapatra from the Department of Physics and Astrophysics, University of Delhi, Delhi, India. Today we are going to discuss about a module named as Instrumentation for Fluorescence Spectroscopy, and that belongs to the chapter named Luminescence under the paper Characterization of Materials 2. So students, let us see what we are going to learn in this module. First, we will learn about the fluorescence spectrometers that provide a tool for analyzing the spectral distribution of the emitted light from the sample, and we will learn about the instrumentation for spectrophlorometry, and lastly we will learn about the application of the spectrophlorometry. The instrumentation provides tool to measure the realistic data of an experimental process. The successful capturing of the experimental events require understanding the instrumentation and implementation of techniques for recording high sensitive signals from a process with high signal to noise ratio. The quantification of the actual data from many potential artifacts that can distort the experimental data is the main aim of a perfect instrumentation. The fluorescence of a material can be measured by fluorescence spectroscopy that detects and records the amount of fluorescence light with high sensitivity. The device that measures the fluorescence are called fluorometers. Spectrophlorometric methods of analysis are the most commonly analytical techniques. The ability of the instrumentation, that the simplicity of the procedure, sensitivity, the selectivity, precision, accuracy, and speed of the technique still makes the spectrophlorometric methods attractive. These features make fluorescence spectroscopy an attractive technique as compared to other forms of optical spectroscopy or other analytical techniques such as chromatography and electrophoresis. The fluorescence spectroscopy has been used widely as a tool for quantitative analysis, characterization, and qualitative control the pharmaceutical, environmental, agriculture, nanotechnology, and biomedical fields. In this lecture, we will discuss the properties of the individual components in a spectrophlorometer and how these properties affect the observed spectral data. These instrumental factors and the optical density, turbidity can affect the excitation and emission spectra as well as the measurement of fluorescence lifetimes and anisotropies. Specific examples are given to clarify these effects and rectify the raw data for recording the original fluorescence data by introducing some technical filters. Light of a specific energy is identified in terms of its wavelength lambda, frequency nu, or wave number. The usual units of wavelengths are nanometers and wave numbers are given in the units of centimeter inverse. The wavelengths and wave numbers are easily interconverted by taking the reciprocal of each value. Generally, The fluorescence spectra are presented in the wavelength or wave number scale. Let us discuss about the fluorescence spectra. When light is incident on a fluorescent material, it excites electrons to a higher energy level. The fluorophore remains in the lowest vibrational level of the excited electronic state for a period of time which is about nanoseconds, generally termed as the fluorescence lifetime, and then come back to its ground state with the emission of a photon of larger wavelength than the incident light. Thus, the fluorescence occurs at a longer wavelength than the observed ones. The energies and intensities of fluorescence give information about the structure and environments of the fluorophore. The fluorescence process is shown in the figure. The fluorescence emission occurs as the fluorophore decay from the singlet electronic excited states to an allowable vibrational level in the electronic ground state. This rapid vibrational relaxation process occurs on the time scale of femtosecond to picosecond. This relaxation process is responsible for the Stokes shift, which describes the generation of fluorescence photons at longer wavelength than the excitation radiation. Then these fluorescence spectra can be of two types. One is excitation spectra and another is emission spectrum. The emission spectrum is the wavelength distribution of an emission measured at a single constant excitation wavelength. The recorded emission spectra represent the photon emission rate or power emitted at each wavelength over a wavelength interval determined by the slit widths and dispersion of the emission monochromator. The emission spectra recorded using different instruments can be different because of the wavelength dependent sensitivity of the instruments. The excitation spectrum is the dependence of emission intensity measured at a single emission wavelength by varying the excitation wavelength scanned over a range. This would represent the relative emission of the fluorophore at each excitation wavelength. For most fluorophores, the quantum yields and emission spectra are independent of excitation wavelength. As a result, the excitation spectrum of a fluorophore can be superimposable on its absorption spectrum. Such identical absorption and excitation spectra are rarely observed because the excitation intensity is different at each wavelength, and the properties of fluorophore, a nonlinear response resulting from a high optical density of the sample or presence of other chromophores in the sample. Fluorometer. The fluorescence spectrometers provide a tool for analyzing the spectral distribution of the emitted light from the sample. The fluorescence emission spectrum includes either a continuously variable interference filter or monochromator. In more advanced instruments, the monochromators are provided for both the selection of exciting light and to detect the sample emission. Such instruments are also capable of measuring the variation of emission intensity for the fluorescence excitation spectrum. Generally, fluorescence spectrometers use double beam optics to compensate power fluctuations in the source. The technique includes the measurement of the fluorescent emission at a right angle to the incident beam. The emitted radiation passes through a second filter or monochromator to isolate the fluorescent peak for measurement. The reference beam passes through an attenuator to reduce its power to that of the fluorescent radiation. The optical paths of the excitation and the detection light paths are along the orthogonal axis. The orthogonal arrangement ensures minimum leakage of excitation light into the detection site. High sensitivity photodetectors such as photomultipliers or charge coupled device cameras are commonly used. A fluorometer provides relative measurement and can be calibrated with a known concentration standard or correlated to standard laboratory models to produce quantitative measurements. Accordingly, based on the technique for measuring the fluorescence, the instruments can be classified into two categories. First one is the filter fluorometer that uses filters to isolate the incident light and fluorescent light. The second one is spectrofluorometer that uses monochromator to isolate the incident light and the fluorescent light. First, let us study about the filter fluorometer. It measures the ability of a sample to absorb light at particular wavelength and emit light at a longer wavelength. It is a good choice when sensitive quantitative measurements are desired for specific compounds. The comparative ease of handling and low cost make filter fluorometers ideal for detecting routinely the measurements. A typical fluorometer includes a light source, a specimen chamber with integrated optical components and high sensitivity detectors, and the schematic diagram of the arrangements are shown in the figure. In the spectrofluorimeter, most spectrofluorometers record both the excitation and emission spectra. The resolution is obtained with changeable fixed slits. The advantage of spectrofluorometers is that they allow for varying wavelength selection. The operator can scan a substance over a range of wavelengths. There is also a disadvantage of spectrofluorometer that it is several times as costly as filter fluorimeter and can only provide moderate sensitivity and specificity. And the block diagram for the spectrofluorometer are shown in the figure. For research purposes, the spectrofluorometer with optical sensitivity and specificity, that containing monochromators with continuous variable slits and a broad wavelength range of 200 nanometer to 1000 nanometer have been preferred. Such instruments have dual excitation or dual emission monochromators for increasing sensitivity and reducing stray light. The instrument fluorometer contains several components, and the main components are light sources, dispersive elements that contain filters or monochromators, and detectors. So, let us study more details about these components. The typical fluorometer instruments that include the basic items of a source of light, a specimen chamber with integrated optical components and sample holder, and also contain a high sensitivity detector. First, let us see about the light sources. The first component of the fluorescence spectroscopy is a light source. It is used to excite the molecule to higher excited state, from which they will lose their energy in the form of fluorescence. Generally, the source must be more intense than that required for UV visible absorption spectroscopy. The magnitude of the radiation emitted is directly proportional to the power of sources. So, a number of light sources can be used to excite the molecule, and the sources are incandescent lamp, arc lamp, laser, mercury vapor lamp, and photodiodes. Different light sources can be used because they provide different irradiation for fluorescence because of different wavelength of radiated energy, such as laser can provide light of wavelength under 0.01 nanometer that provides an immense amount of energy for fluorescence. There is a big challenge to control the wavelength provided by laser because that is so small, while the other way, the wavelength provided by the other sources such as lamps, mercury vapor, and xenon lamps is 200 to 800 nanometer range, which serves different functions for fluorescence spectroscopy. The second component of spectrophlorometer is dispersive elements. To make the fluorescence spectroscopy is a most useful analyzing technique, it is necessary to separate their constituent elements, both the excitation energy from the source and the emitted fluorescence from the sample. So, fluorometers use either interference or absorption filters. Spectrophlorometers are usually fitted with grating monochromators, and there are two types of dispersive elements. One is filters and those are monochromators. Monochromators are used to disperse white light consisting of various colors or wavelength. This dispersion can be done with the help of prism or diffraction gratings. The diffraction grating makes light that enters the grating change the angle depending on the wavelength. This change makes it possible to get the necessary wavelength with the proper adjustment. Using multiple types of filters or monochromators depending upon the type of fluorescence spectroscopy will come out. The primary filters that excite the sample provide appropriate wavelength necessary, while the secondary filters monochromate the emitted light when sent to the detectors. And the third main component of the spectroscopy is detector. Fluorescence signals are usually low intensity, and photomultiplied tubes and diode array detectors are the commonly used detectors. Fluorescence spectroscopy measures optical signals using two types of detectors, single and multiple channel detectors. Single channel detector only detects a single wavelength at a time from a sample, and multiple channel detectors can detect multiple wavelengths at a specific time. The other components are readout devices and the sample holders. The output after getting from a detector is amplified or displayed on a readout device, and the readout devices may be a meter or digital display. To hold the sample of interest, the sample cell or cuvette is used. The material of sample cuvette must allow the excitation or the emission light to pass through it. For an ideal spectrophlorometer, the focus is to obtain correct emission spectra, and the individual components must have the following characteristics. First, the light source must give a constant photon output at all wavelengths. Second, the monochromators must pass the photons at all wavelengths at equal efficiency. Third, the efficiency of monochromators must be independent of polarization. And fourth, the detector must detect photon at all wavelengths with equal efficiency. The characteristics of ideal spectrophlorometer can illustrate in the following figure. Although it is not possible to obtain such ideal characteristics, one could forced to compromise with these components. The above properties are summarized in the following figure. Now let us discuss what are the advantages of the fluorescence. The fluorescence is compared with other analytical techniques such as observance. It is seen that fluorescence is better than the conventional absorption based techniques. This fluorescence is several times more sensitive and selective than observance. More sensitivity arises because the emitted radiation can measure directly and can be increased by increasing the incident power. The fluorescence is also referred as zero background technique, whereas observance is measured the difference between the incident and transmitted intensities. It means signals are measured as a small change in a large background. The fluorescence lifetime can also be measured with high resolution fluorometers designed in both the time and frequency domains. The accurate lifetime measurement requires photodetectors and signal processing electronics with sub-nanosecond precision. In the time domain, femtosecond or picosecond pulsed lasers are often used as excitation light sources. The time delay between the excitation light pulse and resultant fluorescence photon is measured using high-speed electronics, referred as time-correlated single photon counting method. In the frequency domain, the specimen is excited by a light source with high frequency light. The resultant fluorescent signal is also modulated at the same frequency but is phase delay and amplitude demodulated. The phase delay and demodulation contain the lifetime information of the fluorophore and can be measured using heterodyning or homodyning detection techniques. Many fluorophores respond to the environmental changes with lifetime variations. Lifetime measurements are also used to distinguish dynamic and static quenching mechanisms. Lifetime resolved fluorescence resonance energy transfer measurement allows determining the distance between two fluorophores by spectrally resolving the relative fluorescence intensities of the donor and the acceptor Fred pairs. An important example is oxygen concentration measurement based on dynamic quenching of long lifetime fluorophores. For polarization measurements, the polarizers are inserted into the excitation and emission light paths. With the excitation polarizer fixed, the emission polarizer can be rotated to measure the perpendicular and parallel components of the fluorescence emission, and the steady state polarization is defined as the P is equal to I perpendicular minus I parallel whole divided by I perpendicular plus I parallel. The fluorescence spectroscopy is used for various applications such as first one, laser induced fluorescence spectroscopy for cancer diagnosis of human tissues. The laser spectroscopic techniques have the potential for in situ near real-time diagnosis, and the use of non-laser induced fluorescence has been used for diagnosing cancer. Second, the study of marine petroleum pollutants. Here, this fluorescence spectroscopy is used to determine the oil slicks on the water surface and determination of petroleum contaminants in sweater and determination of particular petroleum derivative compounds as well as identification of pollution sources. Third, to accurately determine the glucose level in the blood, the fluorophotometry is used widely owing to its operational simplicity and high sensitivity. Recently, biomolecule stabilized gold nanoclusters were demonstrated as a novel fluorescence probe for sensitive and selective detection of glucose. Also, spectrophotometry is used to study the biological structure and functions. Here, the fluorescence spectrum is highly sensitive to the biochemical environment of the fluorophore, and the fluorophores have been designed such that their spectra change as a function of the concentration of metabolites such as pH and calcium. Fluorescence spectral changes resulting from the solvent relaxation of fluorescent amino acids such as tryptophan and tyrosine are important reporters of protein structure and folding. The protein domain structure and motion on the subnanometer scale can be spectrally monitored using fluorescence resonance energy transfer, generally termed as FRET, which is a non-radiative process where the energy is transferred between two fluorophores. So students, let us summarize what we have learned in this module. The excitation spectrum is defined as the fluorescent intensity recorded as a function of excitation wavelength at a constant emission wavelength, and the emission spectrum is the fluorescent intensity measured as a function of emission wavelength at a constant excitation wavelength. Filter fluorometer and spectrophotometer are utilized to record the fluorescence spectra. The fluorescence spectrometry is used in many areas of biology and medicine, and the filters or monochromators are normally used to remove the pollution or stray light from the wavelength that is used to excite the sample. Thank you.